In this lecture we will discuss the Wittig reaction and ylides. Ylide is a neutral molecule that contains a negatively charged atom, mostly carbon, directly attached to a positively charged heteroatom, usually phosphorus or sulfur. If heteroatom is phosphorus, it is called phosphorus ylide or Wittig reagent. If heteroatom is sulfur, it is called sulfur ylide. For example, this carbon directly attached to phosphorus is an example of phosphorus ylide or Wittig reagent. Similarly, carbon attached to sulfur in these two structures is called sulfur ylide. Let us discuss preparation of ylide. Step 1 is the reaction of triphenylphosphine with unhindered alkyl halide, usually primary or methyl halide. Say for example, triphenylphosphine reacts with methyl halide via SN2 pathway. It forms a salt, methyl triphenylphosphonium iodide. The CH bond, adjacent to positively charged phosphorus, is acidic and can be deprotonated using a strong base. Step 2 in the preparation is thus deprotonation by strong base. The above phosphonium compound can be treated with base N-butyl lithium and ether solvent. What happens is that N-butyl anion abstracts a proton from carbon, which is directly attached to positively charged phosphorus. This generates carbanion adjacent to positive phosphorus. Other side products formed are lithium iodide and N-butane. This carbanion is resonance stabilized. And the other resonance structure can be written with double bond between carbon and phosphorus. This structure is called phosphorus ylide or Wittig reagent. One thing must be remembered here that triphenylphosphine is a bulky reagent and always prefers to react with unhindered primary alkyl halide or simple methyl halide. When we write the resonance structure of Wittig reagent, we see that the second resonance structure, with a CP double bond and no formal charges, appears to be more stable. But it does not contribute much character to the overall resonance hybrid, because the 2p orbital on C and the 3p orbital on P are significantly different in size and do not effectively overlap. The ylide is often represented with a CP double bond, but it is the first resonance structure with formal charges that reflects the true reactivity of a Wittig reagent. It is a nucleophilic carbanion and can react with electrophilic carbonyl carbon. There is a strong evidence that the first step involves a 2+2 cycloaddition process, with the nucleophilic carbon of the Wittig reagent attacking the electrophilic carbon of the carbonyl group, with concurrent formation of an OP bond. The resulting four-membered ring intermediate is called an oxyphosphatane. This intermediate then undergoes fragmentation to give the alkene product, as well as triphenylphosphine oxide as byproduct. The PO bond is a strong bond, and expulsion of this molecule is the driving force for the fragmentation of oxyphosphatane intermediate. Now let us discuss the stereochemistry of the alkene product. Formed during the Wittig reaction, that is whether alkene formed will be having E or Z stereochemistry. Before this, consider this Wittig reagent, wherein carbanion is attached with an alkyl group, which we know is inductively electron donating in nature. Therefore, it destabilizes carbanion or Wittig reagent. In contrast, this Wittig reagent has carbanion carbon attached to electron withdrawing group, and hence it stabilizes the carbanion or Wittig reagent. For example, consider this Wittig reagent, wherein carbanion carbon is attached to ester group. This is a stabilized ylide, because carbanion is stabilized by conjugation of negative charge into ester group. Thus, additional resonating structures can be written for such ylides. Similarly, if the Wittig reagent is directly attached with phenyl ring, the negative charge can be resonated into the phenyl ring, so that additional resonating structures can be written for such ylides, hence stabilizing the carbanion. Thus, to determine the stereochemistry of the product alkene, formed via Wittig reaction. Rule 1 is, simple ylides, or unstabilized ylides, forms the alkene as major product. For example, when we react benzaldehyde with this simple ylide having methyl group attached to carbanion carbon, the major product will be formed with Z stereochemistry. Rule 2 is that stabilized ylide forms the alkene as the major product. For example, when we react benzaldehyde with this stabilized ylide having ester group directly attached to carbanion carbon, the major product will be formed with E stereochemistry. Similarly, if we react this benzaldehyde with this ylide, which is stabilized by phenyl ring, the major product alkene will be formed having E stereochemistry. Consider this ketone being treated with this Wittig reagent. Let us learn how to write the product of this Wittig reaction. First, we will write the resonance forms of the Wittig reagent and show the major contributor with charge separation. This shows the negatively charged carbanion nucleophilic center, which is directly linked with ethyl group. This group doesn't stabilize the Wittig reagent. Since Wittig reagent is not stabilized, hence as per the rule already discussed, Z-alkene is formed as major product, along with the triphenylphosphine oxide side product. The trick to write the product of the Wittig reaction is to swap the oxygen of the ketone with the alkyl part of the Wittig reagent, and keeping the double bonds intact in reactants as well as products. Similarly, take another example. In this case also, ylide is connected with alkyl group and hence not stabilized. The product can be written by swapping the oxygen with alkyl part of Wittig reagent. In this case, ketone is symmetrical, hence E or Z stereochemistry of alkene doesn't matter. Not only aldehyde and ketones, but other carbonyls also react with ylides in a similar manner. For example, as already shown, this ketone, on reaction with ylide, forms this alkene as product. In a similar way, this compound, called ketene, also reacts in a similar manner to form alene as product. Similarly, isocyanate reacts in a similar manner with ylide to form the product, wherein the oxygen of isocyanate is swapped with alkyl part of the Wittig reagent. Same is the case with nitroso compound, oxygen is swapped with alkyl part. Rest remains as such. Ending C double bond N is a masked carbonyl. Hence, upon reaction with Wittig reagent, NR is replaced with alkyl part of the Wittig reagent to form alkene product. In this example, this haloketone upon treatment with PPH3 and then N-butylithium base forms a cyclic alkene. Let us understand what happens in this reaction. The first step is the reaction of triphenylphosphine with halide part of the ketone, via SN2 type reaction. To keep track of bonds broken and formed, always assign numbers to the carbons. This will form the triphenylphosphonium bromide derivative. This, upon treatment with N-butyl lithium base, deprotonates the carbon 1 to form an ylide. We can redraw this ylide. This ylide carbanion at C1 will react intramolecularly with carbonyl at C6. The structure formed is called beta-ene. This forms a bond between negatively charged oxygen and positively charged phosphorus to form four-membered compound, called oxyphosphatane. This will then undergo fragmentation to form alkene, and triphenylphosphine oxide is eliminated as side product. Thus, this is an example of intramolecular Wittig reaction. Consider this ketone. On treating with this ylide, we can directly write the alkene product by swapping the oxygen with alkyl part of Wittig reagent. Since this ylide has an alkyl group attached with carbanion carbon, it is definitely an unstabilized ylide. Therefore, alkene product with Z stereochemistry will be formed as the major product. Similarly, when this aldehyde reacts with this ylide, which is an unstabilized ylide, an alkene product with Z stereochemistry is formed as major product. Consider the reaction of this nitrobenzaldehyde with this ylide, which has an acetal group at the terminal carbon. This indicates a masked or protected carbonyl. We can assign the numbers to the different carbons. The product is formed by forming double bond between carbon marked as C1 of ylide and C4 of aldehyde. This is an acetal protecting group, which can be hydrolyzed with acid to regenerate carbonyl at C5. The acetal protecting group is needed to mask the aldehyde group. Otherwise, the ylide formed would react with itself. Consider this compound. The ylide and carbonyl are present in the same molecule. Therefore, intramolecular Wittig reaction is expected. The atoms involved in cyclization can be marked from C1 to C6. The product is formed with double bond between C1 carbonyl and C6 carbanion. So this is an example of intramolecular Wittig reaction. Similarly, this molecule has carbonyl and halide in the same molecule. We can mark the carbon starting from carbonyl as C1 to C7. The halide is present on C5. Upon reaction with triphenylphosphine, the C5 will be converted into ylide carbanion, which will react with C1 carbonyl. Thus, a cyclic alkene will be the product, with double bond between C1 and C5. Now let us discuss the retrosynthesis of an alkene, to find the best Wittig reagent and carbonyl, which should be used to form a particular alkene. For this, we must keep in mind that ylide should come from an unhindered alkyl halide, because PPH3 is a bulky reagent, reacting best with primary and methyl halides. For example, consider this alkene. Retrosynthesis will always reveal two possibilities to consider. Consider possibility 1. We can show that, across this double bond, this right side methylene is contributed by electrophilic carbonyl, and this left side alkyl by nucleophilic Wittig reagent. Accordingly, we write the possible Wittig reagent in carbonyl, which in this case is formaldehyde. The Wittig reagent can be shown to be formed from the reaction of this corresponding secondary halide in PPH3. Now consider possibility 2. Across the double bond, the right side methylene can be shown to be contributed by nucleophilic Wittig reagent, whereas the left side from electrophilic carbonyl. Thus accordingly, we can write the corresponding ketone and Wittig reagent. The Wittig reagent in this case can be shown to be formed from the reaction of methyl halide and ppH3. We know that ppH3 best reacts with methyl and primary halides, therefore, pathway 2 is preferred over pathway 1. Thus, best synthetic pathway for this alkene via Wittig reaction can be shown as methyl halide should be treated with ppH3 to form triphenylphosphomium methyl halide. This, upon treatment with N-butyl lithium base, deprotonates the methyl to form a Wittig reagent. This can then be treated with this appropriate ketone to form the desired alkene. Consider the retrosynthesis of this alkene. Again, two possibilities would be there. First possibility is, left side of double bond comes from Wittig reagent and right side from carbonyl, which in this case is an aldehyde, propanyl. The Wittig reagent can be shown to come from secondary halide in ppH3. Second possibility is, left side of double bond comes from carbonyl and right side from the Wittig reagent. This Wittig reagent can be made from primary halide in ppH3. Since primary halide is a preferred substrate over secondary halide for synthesis of Wittig reagent, therefore pathway 2 is best. Thus, synthesis of the given alkene via Wittig reaction can be shown as, this primary halide should be treated with ppH3 to form the Wittig reagent. This should then be treated with required ketone, propanyl, to form the desired alkene, along with ppH3O as side product. The trick is that, the double bonded carbon of alkene having more hydrogen, means less substituted carbon side, comes from Wittig reagent. For example, consider this alkene. Left side of the alkene double bond has less hydrogen and must come from carbonyl side. Whereas right side methylene carbon must come from Wittig reagent. This Wittig reagent can be shown to come from methyl halide in ppH3. We can explore the alternate possibility also to see we are correct. That is, consider that this left side comes from Wittig reagent and right side from carbonyl side. This Wittig reagent can be shown to come from primary halide. Method 1 is more efficient, because, in that case, Wittig reagent comes from methyl halide. Then method 2, in which Wittig reagent comes from comparatively hindered primary alkyl halide. Thus, synthesis can be shown as methyl halide should be treated with ppH3 to form the Wittig reagent. This can then be treated with aldehyde to form the desired alkene. Thus, this methylene side having more hydrogen comes from Wittig reagent. Same trick can be applied to find the best Wittig reagent to synthesize this alkene. This right-sided carbon is not having any hydrogen and thus comes from carbonyl reactant. This left-sided alkene carbon has one hydrogen and thus comes from Wittig reagent. We can show the retrosynthesis like this. Left side from Wittig reagent and right side from carbonyl, that is cyclohexanone. The Wittig reagent can be shown to be formed from reaction of primary halide with ppH3. Thus, complete synthesis via Wittig reaction can be shown as benzyl halide is treated first with ppH3, then with N-butyl lithium, to form the Wittig reagent. This can then be treated with cyclohexanone to form the desired alkene.